Hi, I'm Yaku, and I was intrigued by the video that Veritasium put out, and of course, then especially the comments of all my usual YouTubers that I follow. Bob was had a very good contribution to that problem, and Mehdi had one as well. Quite like that. And then, of course, Alpha Phoenix's experiment made me think, but I can do that, and I have more questions. So one of the biggest questions that I had was quite simply, a lamp needs current. I need this um, I need this experiment, this one, to be done with real current, meaning in excess of an ampere at least, so that we can understand what is happening. I like the presentation that Alpha Phoenix had on his oscilloscope, but that seemed to me, that wire seemed so thin. It seemed like, um, yeah, I like to see things that actually have real current flowing. So that's what I then decided to do, to actually set up an experiment, and that's what I did. I went out to buy some thicker wire, uh, um, 16 gauge in the American language, or 1.5 square millimeter copper wire, standard PVC insulated wire, which I then rigged up in a situation like this. Um, I actually bought more, and I did some more experiments. I bought a kilometer of wire, so I rigged it up in various ways. And when I had to redo it the first time, I realized that it's no fun running out the kilometer a kilometer all the time, and my oscilloscope is sensitive enough to actually just use a quarter of that. So the follow-up tests were all done at 125 meters running out and back. That's a 250 meters loop that I had there, in a situation like this. I actually rigged up a little lamp as well, but measured that on the oscilloscope. It just is too slow reacting, so I don't even have this on this presentation anymore. It is still on my test board, but I don't use it. It's simply too slow. As Alpha Phoenix also did, you replace the lamp with a resistor, and off you go, and then you can actually accurately measure when the current arrives and when not. So that's what I did. There's a picture of one of my little test circuit down there, and you can see the wires running out. That particular example on that day was a 500 meter out and 500 meters back. That's a kilometer of wire, but I did a few of them. So anyway, so I'm going to talk about the 125 meter wire in this presentation, and we now, after seeing all these contributions, we know that there will be a portion of the current flowing in a wave this way, and a portion of the current flowing in the jumping the gap, as it were, across the insulation layers, and arrive at the lamp very quickly. So my question is, how much and how fast? So that's what I set out to do. So the spoiler alert is, here's the results. I don't want to make you sit through the whole video. If you can just look at the results. So my test result is in red there. The first immediate contribution is a tenth of an ampere on the setup that I have. You will see the setup later on. It's not relevant right now. And then there's a stepwise increase in current as time goes on. Of course, that is due to the wave bouncing back and forth from the source to the remote end. And I've got the times over there. So it goes to a quarter of an amp after 1.16 microseconds, goes to almost 40% of an amp going after 2.3 microseconds, and then half an amp after 3.5 microseconds. And that goes on. It ends up at the cohesion state of which you can calculate with Ohm's law, 3.2 amperes, and that it reaches after about 100 microseconds, which is 0.1 of a millisecond. So that's quite quick. So nevertheless, that's the results. And if you want to see how the the graphs and things, I will show that to you. Otherwise, well, thanks for watching. Anyway, I do also have a nice little test which I will demonstrate while we talk. Sitting in the office over here, of course, I'm not demonstrating. I'm not taking out the whole office and the video and everything else like Alpha Phoenix did. I will show you the results, but I will do a test in the office over here as well. So, first of all, we are going to talk about my contraption that I built there. So, I had the wires, of course. This is the wires that I've indicated over there, 1.5 square millimeters. Copper conductor. I am measuring the voltage as I'm entering the lines. So I will see the voltage which is presented to the lines directly. So when the switch closes, then the battery pushes the charges, and I'm an engineer. We work in charge movement, even though we all know that hundreds of years ago already we decided to knowingly use charge. Well, we know it's electrons, but I'm not. In this video, we charge positive charge flow. That's what we're working with conventionally, right? So the switch closes. The positive terminal of the battery, the red one over there, pushes the charges into the lines, and I'm getting the voltage as it enters the lines. There's a short circuit on the far end of the line, which is very much in agreement with Veritasium's original setup. And what's even more, instead of the lamp at point B, I'm measuring the current exiting from the return lead, return line. Then, so I'm measuring current through that. So now what we will do is we'll just transfer that to a more realistic little sketch, a schematic sketch of what I'm actually doing. So I'm putting a 12-volt battery, measuring 13.05 volts, no load. There's an internal resistance in there that I've measured, which is 0.091 ohms. And then there's a switch. Instead of my red voltmeter over here, I'm using the red channel into my oscilloscope. So at point A, I'm feeding the voltage with respect to the black wire, of course, as Bob would always say. It's always with respect to the black probe. Black probe is on the return lead. So I'm measuring the voltage entering the line, right? And now it comes out of that transmission line, and it goes through my measurement resistor. Now you'll note that the measurement resistor I chose to be 1 ohm because it's very convenient, because every volt that you measure on point B of the oscilloscope would then correspond to 1 amp. This resistance of the copper loop, the 250 meters copper loop, was measured to be 3.02 ohms at that temperature of the day. The first thing we're going to calculate is what will the end current be once you have flipped the switch and all the effects have settled. On Veritasium's example, the current has gone through the end of the universe and back. Well, just jokingly, it's gone 300,000 kilometers away and back. And what would the final value be? That's to be calculated by Ohm's law, and we quite simply take the voltage of the battery divided by the sum of all the resistances in that loop, and we get to a value of 3.17 amps. So that's a significant amount of amps. That's what I set out to do. I wanted to have a hefty circuit which would be fairly robust to stray currents and stray capacitances and measurement deficiencies. So we closed the switch, and I immediately reopened it after 10 microseconds. So that is an on-off pulse that I'm registering over there. So what am I getting? I've alluded to that in this just after the spoiler alerts in the beginning, that we have a stepwise increase of current. So the first step is, of course, over there. Second step, third step, etc. The first step value will depend on how much current is actually flowing through the gap. In order to calculate that amount, we have to go back to the pioneers of the telegraph. A certain Mr. Heaviside parameterized that very nicely. There's lots of writing. You can go find his original manuscript as well. I found that somewhere. We've measured that to be 103 milliamps. Yes, we've done that. I have now over here. You can see that I've put down a value of 136 ohms. I'm not going to go through in this presentation with that. I will put a calculation up how I get to something between 127 ohms and 140 ohms of resistance over there. I'll put that in a link. So nevertheless, 136 ohms, if you do the same type of calculation which we've done before, which is then the 13.05 volts in the loop, the 0.91 internal resistance of the battery, the 136.1 ohms calculated to be the transmission line characteristic impedance, and then the 1 ohm measurement resistance. So then you get to a calculated value of 95 milliamps. So, and that's measured to be 103 milliamps, which is not a far side off. If you follow through the telegrapher's equations and the theory of the transmission line theory, then you can actually start calculating these further steps as well, and which I've done. If you look at that, that's done and plotted. So you could see that I could calculate or predict what these step values would be. Now, these step values, of course, being just a pure enlargement of this area where I'm circling there at the moment. So you can see those are the values that I indicated right at the beginning of the video, in this or just after the spoiler alerts. So those are the values, and that's why they are going up in those steps, and those steps are quantifiable, and it's because of the wave going through this transmission line to the end, bouncing off the further side, coming back, grabbing more energy, bouncing back, and charging the transmission line to get to the final value of 3.17 amps. So just a little summary of that: 103 milliamps immediate current, and then it goes up as we've indicated before. I was wondering how a rolled up transmission line will perform. This particular one is my 250 meters wire, which is a pair. So that's a 125 meter long transmission line rolled up on a plastic reel. This is called a bifiller coil. Both parts of the pair of wires are then rolled up onto the coil simultaneously. So what that does is the magnetic field around the one conductor gets cancelled out by the magnetic field coming back in the other conductor, which means that this is a almost induction-less coil. So this is used for inductance-free resistors, wire-wound resistors that are doubly wound like this in a bifiller way, to make sure that that you don't add inductance to the resistor. Anyway, so what will that do? Let's look at the conventional transmission line and the analysis thereof. So you'll have the infinitesimally small sections of inductance and capacitance circuits there. This, of course, is the lossless model, where there's no resistance in the model and no resistance in series with the inductor, and no resistance in parallel with the capacitor. So if you look at the transmission line model over here, that is the normal one. What will happen if we add if we wind this thing in the bifilar way? Let's draw it out and see. So you are now coming around with the same conductor, and what is happening is the conductors, the adjacent windings, are now close enough together so that the capacitances in between those conductors are of similar magnitude, or at least order of magnitude, than the ones in between the pairs of the transmission wire, so the transmission line. So what you're actually doing with those little green capacitances there is you are bridging out the sections of inductance. Well, in real life that would be sections of induction and inductors and resistors, but this is just an LC circuit, and we all know a parallel LC circuit is just a resonant circuit. So what I expect is going to happen here is we're going to have some funny resonance effects here, because there is just plenty capacitances added to the already inductive circuit. So, and this isn't part of the analysis, and we should be seeing something very, very weird. If I want to test this, of course, then I just put this bifilar winding instead of my transmission line. So, but what do I see there? Those green capacitances are the ones that I've previously indicated. But remember also, the coil is such that the top layer affects the layer underneath it and affects the layer underneath that. So there's a whole lot of extra capacitances that we're not aware of normally. That's not normally there. So I've tried to indicate with the yellow lines there some additional capacitances. Now what the effect of this would be, in this case, when that very, very fast rising pulse comes along this line, you will find that there's capacitances connected from the input of the circuit to the local end to the remote end, and then back from the remote end back to the input, and all sorts of capacitances in between. So when you send that step function, you have a very, very small delta t, and therefore you will have an excessive current into that first pulse. So that's what I'm expecting to see when we do this. So let's do some testing. My test kit that I have corresponds with the circuit diagram that we've been talking about all along, and I can just point to the right components. There's the battery, of course, and this is the battery. We have the MOSFET switch over there. There's the MOSFET. We have the switch controlling the MOSFET, is that one? It's there. And then we of course have our oscilloscope that has its red and its blue inputs, and it corresponds with what I have over here. So the red input on the oscilloscope is the voltage applied to the transmission line. The blue input is the current returning from the transmission line. So with that said, let's do some testing. So I've set it up like this at the moment. I'm first going to do a slower capture with a long time, so that we can see the DC component. So I'm going to purposely let it run until the DC is evident, so that we can see what those values are, and it should be similar to what we've previously calculated anyway. So what we're going to do is we're going to hit the on signal and off again, and we can immediately on my oscilloscope see that we're looking at 3.13 ampere, which is more or less what we expected. So that's good. So I've got my oscilloscope program here. So let's just get a better recording view, at least. Right, there we go. So what we have, 3.13 ampere, and you can see how that is increasing up to the 3.13 ampere level. What you can also see is the switch on of the switch. It remains on, because it's that MOSFET circuit. It remains on until you switch it off. And positive and negative pulse. At the very beginning, as I suggested, that the capacitances in between these things are creating an instantaneous short circuit for that step pulse coming in. So what we're going to do is we're going to do another shot, because we're going to look into, we're going to decrease the time base of 10 microseconds there, so that we can see what's happening in this portion of here. This is the typical transmission line step response. Let's see what happens. So we can go, and again, all right, and we can already see there's a bit of a mess there. We did expect that, more or less. So let's import that. Right, exactly what we expected. Now we can see those steps. You can see those steps, and it's increasing by every step. And we can also see this massive impulse in the beginning. So it's not only one impulse, but remember, when you are in an inductive and capacitive environment and you fully charge up a capacitor because of the mechanism which I've indicated, it's a step impulse coming in, and series capacitors are right through from shorting out your input, with inductances in between, a little inductive cells, as we spoke before. Then you will no doubt get some resonance, some various resonances in there. So we do have some indication of what that frequency could be. So let's just do some measurements over here. 4. So that's 4 cycles, 300 nanoseconds. Let's check that out. That is 13.3 megahertz. So let's go back over here. 13.3 megahertz. Very high for that situation. What we are expecting in terms of the wave going back and forth on the transmission line is 1 microsecond per division. So we're looking at about 1.5 microseconds, which is in the region of 600 kilohertz. So a massive difference, and that's due to the additional capacitances that we have. That is we have now zoomed into the switching on part. What I also want to do is I want to switch off that current again. So what you have is you have a DC current of 3.1 ampere, and when you open that switch again, that 3.1 ampere will most certainly want to keep on flowing, because the magnetic field is fully expanded and it will be contracting. So the moment that magnetic field is contracting, then you will have some induced voltage back and forth. You are expecting some issues, and this time I'm going to not make use of this switch. I'm going to make use of the mechanical switch, which switches on and switches off 10 microseconds later. So this is this switch. Okay, there we go. And let's load it. This is what we have. A big mess. Let's go through the various aspects of this recording. Previously, we had this portion, which is the switching on of the current in the transmission line. We have the steps, and then before it reaches the maximum, long before that, 10 microseconds after switch on, then I switch that off. You can see that in evidence of the voltage trace. This is the voltage going into the transmission line here at point A. So that is switched off. And what happens there is at that moment of switch off, there's a lot of energy in there. So that energy wants to go somewhere immediately. Immediately it goes into a massive pulse again, and charges up those capacitances and discharges. So these additional capacitances that are added in this bifilar winding is causing this very, very highly active discharge. You can see that. But in doing so, there is a 10 megahertz plus oscillation happening inside within this coil. I want to zoom into that little area. I want to see what that looks like. So energize, right? That is the beginning of that discharge cycle. You can clearly see the initial high pulse and the pulses following that. Allow me to recap what we have seen and done in this experiment. Let me quickly recap that. So first of all, we consider the original question by Veritasium, and we understand the two modes of current a lot better now. So there's a portion of the current that directly crosses the gap, and there's a portion of the current that goes in a wave action around here, bounces back and forth, and stabilize until you get a DC value. We've also quantified those values. We saw that Ohm's law could give us the DC value, the DC equivalent after everything has settled. We also saw that Ohm's law, again, with the telegrapher's equations, can give us the quantum of those steps, those wave steps that we are getting. We can also see how fast that is. Speaking of the speed of that, this little time period there, then that reflects to 1.2, 1.25 microseconds. That is a lot slower in the case of the bifiller winding. So when the transmission line is rolled up, then all of a sudden that the wave moves slower. When you wind that transmission line in that coil, you are forcing the waves to move through solid PVC, as opposed to when you only have two conductors and it's surrounded by air. The medium, the insulation medium, is actually PVC and air. So the wave speed is determined by the medium through which it goes. If you look at the experimental time that I found there, or that I calculated, then that reflects to 0.68 C, and in the bifiller case, it's slower. It's 0.55 C. So that's a nice measure that we could also figure out from this experiment. Okay, what else? We also with particular attention to the bifiller winding, we have seen that I have predicted that there's going to be a spike. There is a spike when you switch the voltage onto a rolled up transmission line, and the reason for that is the interwinding capacitances that causes that spike. We also see that the spike is there. There's a little bit of a ring down after the spike. Then there is the usual waves back and forth, building up to the DC value at the end. When the switch opens, the moment the switch opens, the geometry of the transmission line changes, because there's an open circuit on the source side now, and you find that there's those LC cells, due to those parasitic capacitances between the windings, are making a big mess there. And when this rings down, it's actually easier to show it on the standard transmission line. When you start decreasing the current due to the switch that has opened, once you have to reach zero, because there's resistance in the system, and everything will dissipate to zero. You have to reach zero. When you do reach zero, there's an overshoot over there. That overshoot is a bit of energy in the system, and what happens is that energy forms a wave and runs to the far end of the transmission line, comes back to the close end, and runs back and forth until the wave has dissipated in the resistance. That makes us think what's going to happen in Veritasium's case, where you have superconductors where the waves won't dissipate. Anyway, it happens that this resonance has a period of twice this this wave time, and the reason for that is you have an open circuit on the one side, which is the battery side, is an open circuit, and you have a closed circuit on the other side. And if you follow the waves and how they bounce back and forth, you will see that the wave has to get back to the original source, for example, red wire, before the cycle restarts again. So that's why the period is double that. I think we've covered everything that we've done. What a fun experiment, and thanks for listening.